mean, the matrix solver is not iterative, right? I mean, these two are just kind of you get
yeah,
the.
In terms of
oh, this one.
computation and
it should be on the order of n. I think ideally these two.
Of the order n.
Yeah, but I think the scaling can be pretty bad. I mean, the constant coming in front might not depend on n, but might be extremely high. So what I hear is that effectively, even though multi-grid solvers, for example, scale on the order of n, they would be somewhat slower than FFT methods because they are more elaborate. You have to do a lot of things. You have to interpolate from different resolutions.
Right. There are some cloud tricks to sort of jump ahead because of course the potential doesn't change dramatically from one step to another. So for
yeah.
a lot of it, yeah, that's the most important.
Yeah, you already have a pretty good initial guess of what the potential is. So, but kind of, yeah. So we decided to go actually and implement an FFT method. So it works on an equidistant grid with periodic boundary conditions, and I think this is very much in the Pentecost spirit.
I profess it's not.
But traditionally, this is very much the Pentecost spirit. Local boxes, local Cartesian boxes, maybe with the zero boundary conditions. So normally with periodic boundary conditions, right?
No problems.
And it's also suitable not only for periodic boundary conditions, but also for shearing sheet boundary conditions where the boundaries are sliding relative to each other. So I will come back to that. You have to do some slide modifications, but it's definitely possible.
I mean, what are you saying? You're saying it's not your problem, or what do you say? It's not the kind of problem that I deal with. You know,
I mean, is that true? It's maybe not true even.
Maybe not true.
I mean,
maybe one could do.
But basically what you're saying is you need a Cartesian box, right? And are you saying you're not doing a Cartesian box?
No, it's boundary conditions.
Yeah.
But
even then, you can take care of that.
But it would be a very funny global accretion disk that would fuel a number of copies of itself situated all around it in space, right?
Yeah, but you have to do, I think, some patches on the density. I mean,
patches.
So that I mean, Åke told me one thing, one trick one can play.
Okay.
So that one can actually use periodic boundary FFTs.
So how does Åke has also solved self-gravity for accretion disk, right?
Yes.
And he does it with an FFT method, or does he use
FFT, of course, yeah.
Okay, so he must assume something with periodic boundaries, or have some kind of.
I mean, yes. I mean, it really has something to do with the shape of the potentials of the. So, I mean, I need to think about this again.
But then there are some other things there in the manual that says that currently works only for cubes.
What?
Which means for
cubic matches. Only works for cubes.
Yeah, FFT only works for
slabs. Something.
Yeah. That's just a minor problem. I mean, that really has to do with the
minor problem.
No. Yeah, because you know why? That has to do with the transpose operations. So if you do a transpose, you want to reuse ideally the memory that you have, and if it has the same size, it's all very easy. So then we thought, okay, should we go for the easy thing and just try it out? And it has the same size.
So it's a matter of memory efficiency. And if one was to relax this, one could easily make it work for any relation between the.
But the problem is that what you actually have, the standard solution, the proves in the other day, is that actually what you then do is you take the minimal cube that your thing fits into, you store the whole thing and transpose this fake thing, right?
Yeah.
That's it, and it's.
Yeah,
you've got a
exactly.
slab which has got an aspect ratio of 10.
Yeah.
That means you end up with 10 times.
But only for one variable. And we are very, very, very rarely limited by memory.
Yeah.
Right? I mean, except if you use the iPhone compiler sometimes.
And regarding boundary conditions again, I mean, as long as we use symmetric or antisymmetric boundary conditions, it is still, it can be turned into a periodic one.
I think that's okay.
If you use symmetric and antisymmetric, you say.
If it's symmetric, for example.
Yeah.
Then the grid point on the left is actually the same as that on the right.
Yeah. That should be okay. Yeah.
So one could just do it and test whether.
I think that would be the way. I mean, just try it out and see if it gives something reasonable or not.
There's one other thing that I think maybe you're going to mention, maybe you have thought about this. You have to subtract, I think, the average density, right?
That's a very, very good point. So when you solve the Poisson equation, you realize that you can only solve when you solve the Poisson equation with the Fourier method, you realize that the constant mode can never give a solution. So you have to disregard the constant mode, and that actually it's just a matter of when you solve for. We take this equation, you just forget about k equals 0, because that will not, with periodic boundaries, it's not supposed to give you anything. It doesn't change the potential. The only reason why things are more unstable when the background density is higher is that the pressure gradient has more trouble moving things away from collapsing regions. It's not that the potential or the self-gravity becomes stronger, because it's just an infinite space of constant density that doesn't have a potential, right? So it's kind of an interesting way of thinking about it. But that's actually the Jeans problem. That is exactly the Jeans problem in infinite space. And I'll also show some of the test problems. Anyway, once you use the FFT method, the only computational difficulty left is actually that you need to do a lot of parallel FFT. So you need to find out how to do parallel FFTs efficiently. And the great part is that Axel, I guess you and Liz had already implemented this more or less for the power spectrum. So the idea is that Axel says do the FFT in the x direction, which is present. You have the entire x direction. Then you transpose the entire array so that y comes in x, and then you FFT in y, and then you do the same with steps. So all that's left is to that you have a lot of parallel communication there. So, and also the power spectra, we had to generalize them both to do inverse transforms. That didn't work very well. That was
well, I think it had been started and never finished.
Yeah.
So
it had never been used.
And it was sort of wrong.
Yeah. And we also had to make them work with shearing boundaries. So I'll come back to that probably.
For what reason? You mean this I actually don't recall. You said there was something for the return transform already implemented.
Yeah.
Yeah, but it wasn't really.
But it didn't really work. It looked like someone had started it.
Yeah.
I think Tarek and Nils started something for it was for initial conditions or something.
Yeah, it was. It was only used in one of the initial conditions.
Yeah.
It was parallelized.
Or maybe actually
What's that?
It was parallelized, yeah.
Well, sort of. No, it wasn't parallelized.
Yeah, then I know that. Yes. Okay.
Yeah.
Okay, so this is the famous Jeans problem. I just want to go through some test problems. Jeans problem in 1D with periodic boundary conditions. This is just the linearized equations. So it's just the velocity changes due to the pressure gradient and due to the potential. And then you solve on top of that the one-dimensional Poisson equation and the continuity equation. And you can solve it linearly and get this nice dispersion relation, and then you can try that with the code now, and you get a function of time, the maximum density. So here we started with a density perturbation of 10 to minus 6, and it goes very nice and very linearly, exactly as predicted by Mr. Jeans. And we actually added that as a sample. Is it auto-tested for? I guess it's not.
I don't remember. I thought we did edit the auto test, but I'm not certain.
So we added a lot of there are so many linear problems for the self-gravity that we actually just more or less added all of them to the samples. But I'm not sure that they should all be auto-tested for, because yeah.
As we discussed yesterday, one reason to auto-test them on a monthly basis would be to maintain the validity of the input files.
Also, I mean like having a giant auto-test, a small auto-test and a big auto-test.
Yeah.
But that's a very good idea.
I mean, I just came across another problem this morning which didn't work whatsoever, which was also in the samples to the convection.
Yeah, that's actually because then you could say that you can do an auto-test on everything and has a reference .out.
Yeah. My problem didn't even have a reference .out.
Okay.
But it was still in the samples.
Yeah.
And it was it's now completely broken.
It didn't compile anymore. So.
But the stuff, I fixed already, and it's still not correct.
Anyway, the next problem one can try is then a tumor problem, I guess you would call it. So that's just the Jeans problem, including the one-dimensional Jeans problem, including Crowley's force and shear. Shear in in the sense that this would normally be a 2 in the Clodagh tortoise, that 1/2 is just the advection of the Keplerian velocity profile as you move vertically outwards.
Oh, there's a sign problem.
Hmm?
There's a sign problem? It must be plus 1/2?
It should be plus 1/2, yes. No, this should be plus 2, this should be minus 1/2.
Something like this, yeah.
This minus is wrong. Yes. And then you can again solve for the dispersion relation, and it looks almost like before, except there's a capital omega coming in here stabilizing things. So rotation and shear stabilize a little bit. It works effectively like an additional pressure. And then again, as long as time, here's the max of rho, and this is the analytical value, I think, and this is the actual value. And the reason why it starts to diverge is actually that you get into the nonlinear regime here once rho prime becomes on the order of 1 linear theory breakdown. So this is another test problem that we call Tumor X. Okay, so shear boundaries. So this is a figure from Hawley and Galley and Volvus 1995, and it shows, of course, what we probably all know, that if this is the radial direction and this is the computational domain, then a goldstone here shouldn't be set from the value here, but from some kind of value that is shifted. So they're not strictly periodic, and that's why it's not. You cannot really just do the Fourier transform along the x direction in the shearing problem, because the x direction is not periodic. I don't know, did we ever do that? I mean, I did it for one publication at least without thinking about it.
What?
Just doing power spectra in the shearing box, and I mean.
Yeah. I mean, we also did this, and I looked at the animations, and they're on the web, and I think you see some fluctuations at high Beck numbers.
Yeah.
And then you can basically see, maybe at least hope that everything at large scale is unaffected by this.
Yeah, that's true. But the thing is with the high wave numbers, that then it's not certain if it's like small wiggles at kind of small scale, or if it's something with the. I mean.
Yeah. Right.
So.
Shouldn't this non-periodicity in the x direction cause a spike at low wave number? Because it's not periodic, so there should be some amount of power. I thought if you did this, you'd get a funny bump somewhere near the size of the box.
Well, no, you get, so if you've got this kind of, if this thing, if you take your periodic thing and put it here, and it's not quite periodic, what you actually get is a little kink.
Yes.
Oh, local kink.
Yeah, sure.
Right?
Yep.
So it's
Which
right on the left scale.
Which is extremely small scale. So you get some excess small scale power. Anyway, Charles Gamble in 2001 did a paper where he outlined how you can solve the Poisson equation on a shear periodic grid. I'm not even sure who's the first to do this numerically, or if someone tried that before.
I mean, OVP has certainly programmed such a thing already in the early 90s.
Ogilvy? Okay.
Or mid 90s, yes.
Okay.
And as I said, I mean, this technique is known to those people who know it, and these are the NASA Ames, for example.
Okay. And of course, it's been known analytically. I mean, that's what you do when you do the stability analysis, and the old Goldreich, and Littenbill, and Tremaine, and all
but
that.
The FFT method is actually known.
So actually, what you do is that so FFT with shear boundaries, that first so this is just a plot of the density. So as a function, this is then x and this is y, and you see here it's shear periodic. It's shear periodic with a shift of half of the box size, right? So this point becomes periodic with this point, I guess, right? With this point, not with this point. This point becomes periodic with this point, right? And this point with this point, so on. So what you do is first you Fourier transform in the y direction, because the y direction is periodic already, and then afterwards you shift the y direction so that the x direction becomes periodic. So you more or less take so each of the y tensors here, and then you shift them down in a way that is that depends on the distance from the center of the box. So this one is shifted a lot, and the middle is not shifted at all. And then you can make the entire box periodic. Actually, actually in Charles Gammi's paper he shifts in a way. He actually just starts by reinterpolating everything going on in here so that it becomes periodic in the real space. So he would immediately take and just shift everything with some high order interpolation. But actually it's much more wiser in a way to do this in Fourier space. Because once you are in Fourier space you can do interpolation of order in nx almost free. It's just that, I mean, yeah. So it's actually something that was pointed out to us by Colin McNally on his webpage. So yeah, so you Fourier transform the y direction. Then you just in order to shift the y direction afterwards you just multiply each amplitude by a complex amplitude that will effectively shift that y pencil. Then you Fourier transform x direction. Then you Fourier transform z direction. Then you solve the Poisson equation, and then you go back the same way, and you end up with a potential that looks like this. So you see that the potential is high, is positive, while the density is negative, kind of what we expect of, right? And you notice there are no artifacts of the boundaries here or anything. If you hadn't taken into account the shearing boundaries, this would never look that nice. You might get something nice in here, but it would look really awful out of the boundaries. If you think there was a lot of power on small scales, not the case. It would not work.
This interpolation trick, one could perhaps also use in the actual calculation of the shearing sheet boundary condition of setting the ghost zones.
We thought about that actually.
Yeah.
Yes, you could effectively in the shearing sheet do instead of 6 order interpolation, you could do an nx order interpolation by So you have to basically you have to take each y pencil basically and then Fourier transform it and then just multiply it by some kind of complex constant that would then move it. But so do we want a higher interpolation order in the shearing sheet? I mean, I sometimes see things at the boundaries.
Yes.
It's not going unnoticed by the code that there are shearing boundaries at least.
Yeah, right. It's less accurate certainly on the boundaries, and you also see this, but only when we really reach the resolution limit.
Yeah. So yeah, I think it would be worthwhile thinking about.
So in that case, would it be best to have the shearing sheet actually the other way around? So you only need a Fourier transform in one direction, right?
In the shearing sheet.
Yeah.
Oh, that's what you mean, like turning it around.
If you were to do a Fourier transform based shearing sheet, you would want to be the y pencil, but you need to transform. You would really like the x pencil.
Yeah, but it would be very confusing to turn x and y around. Some people do it actually, right? I think I remember when I worked with you and Anya here, there were some papers where they had x being the azimuthal direction and y pointing inwards or something.
Of course, the other solution is to have ny proc equal to 1.
And the third solution is to
you could have a very quick sort of a quick fix that you only have a parallelizing z.
And then
that's actually the way most shearing sheet codes are. There are very few shearing sheet codes that are parallelized in both directions.
Exactly.
And we know why, because it's awful. it's difficult to figure out
what really fun to write it, let me tell you.
Yeah.
The double interpolation across processors and across ghost zones.
Yeah, that's very strange. Yeah,
but for the x, if you just do FFT in the xy plane, then you could just use the WFFT, of course, or FFTW.
FFTW, yeah.
Which could be.
But that's only slab parallelization.
Yeah, that's right.
Yeah.
Which is what we just discussed, right? We just parallelizing x and y in D.
So how fast is FFTW compared to our FFT?
It's supposed to be the fastest, right?
Yeah.
It is. It's really fast.
So we could buy a factor of 10 by having a better FFT than
Factor 10? That's a bit much, but
okay, 2
or 3 sometimes. It depends on application to application, and if you do you have to pull out all the FFTW tricks to get it. But they're pretty easy to pull out. I mean, the whole point is for it to be really, really fast, but not too painful to crank it up.
So their core FFT, even without parallelization, is done in a way that makes it faster than a normal FFT.
Yeah.
Okay, cool.
Yeah. Yes, definitely.
By keeping track of some things and
Well, by adapting to the processor that you're on. So
oh.
it gathers what it calls wisdom, which gives it a little bit of advantage in tweaking the way the FFT works. That's my understanding, and I have a pretty poor understanding, but I have tested them.
I got the it is problems with them. It's actually things like cache efficiency,
Yeah,
for
exactly.
example.
Oh.
It really says, because when you do FFTs, you're always dealing with these long 1D things.
Yeah.
And it's really horrible. One of the worst things you can ever do is have a number, if your cache is this big, you want to deal with 1D things which exactly fit in the cache. What you definitely don't want is to have 1D things where you get 2.5. It's better to it's better to actually do 8 things than 4 things if it's going to solve this problem. Yeah?
Yeah. I'm just still
That's exactly it, right?
Yeah. That's pretty much
Sometimes it's actually better to half the size of the thing you're doing and get nearly more of them in. But there's a limit. So if you divide it by 16, then you're doing too many things.
Yeah.
So it's a slider between how big an intensity you have and how big
I'm just confident. Yeah.
But the nice thing is the interface to FFTW, of course it breaks the pencil code rule, right? Required depending on FFTW.
Well,
but we always do. We always have external FFT libraries.
Oh yeah, I know.
So
they're not external.
Well, it's a source code library though, right? You get it as source code, don't you?
Yeah, sure.
So we can CVS import it, and we can have a vendor supplied thing that's simply you know the idea of done better in SVN.
Yeah.
But I don't think there'll be too much objection to a source code thing which can literally be committed with the code and is in one place.
Yeah.
The whole point of the rule is it should be a one-click make. It shouldn't be download.
But the FFTW would be optional.
Right.
You will still always revert to the numerical recipes or FFT pack or whatever we're using, right?
I mean, you'd have to be doing a pretty big run to justify using FFTW if you're building it from source all the time, because it takes a long time to build.
Well, that's just a question of having the makefile set up correctly and make sure it only builds it when it needs it, and when it builds it, it only builds it as often as it needs it.
Right, yeah, sure.
It's fine.
Yeah.
But that should be done.
Yes.
I mean, I agree. We've been talking about FFTW for 3 years, I think.
No, it's really good. They're really smart people and they've done a nice job.
Yeah.
And we should use FFTW 3, which is the new version, which is not backwards compatible with the old one, so nobody uses it because they all want to keep using FFTW 2 so they don't have to rewrite their implementation. They sort of rebooted with FFTW 3, but it's much better.
Cool.
Alright.
What's copying in the meantime? No?
So I just want to show a movie actually of what it looks like for a 2D test problem with the shear. And here we actually take a self-gravitating sound wave in 2D with shearing boundaries. And this actually is such that even without self-gravity, this sound wave would be amplified. So I think this is what people sometimes call the swing amplification. Right?
I missed that.
If you have a non-axisymmetric sound wave in the shearing sheet, which is being sheared, that means that it is being rotated and it's kind of becoming narrower and narrower.
Yes.
It will increase its amplitude.
Yeah.
Up to a certain finite value. It's not an instability as such. It's just that
Transient amplification.
it's a transient amplification, but this amplification is made larger by the self-gravity, of course.
And then it can become unstable.
It could become unstable, but it very quickly goes to so small scales that you have resolution trouble.
Yes, but in reality,
yeah. So it's actually the same as the tumor problem, only with the same title, and only there's the shear term here also. So you assume you start with an initial condition where ux and uy depend on y. And maybe I could just try to show a movie and show the first slide to show the initial condition. This is the initial condition, which is the density. And you can see here that it's a non-axis symmetric wave from the beginning. So it has what does it have? K kx equals -1 and ky equals 1.
I think that's right.
This is a kx equals -1 and a ky.
It's a 45-degree wave then.
Yeah.
So it's a what we call it's a trailing wave.
That's a trailing.
It's a leading wave.
Leading wave, yeah.
It's a leading wave now that will be sheared to become a trailing wave.
But you could have started immediately with kx equals 0, no?
We could have done that, but we wanted to see the amplification, so.
And this is kind of the standard
We
thing.
wanted to go from leading to trailing, so that's what we had.
And this is what they like to have in the analytical papers, my impression also. Because
Well, that's because that's where you get when you cross through that kx equals 0 point.
That's a stronger amplification when it goes from here to here.
Yes.
So I'll just show you the movie that there are no artifacts at the boundary and that is actually solving the equations.
Okay.
So there are artifacts at the boundary here, but this must be something with the movie player. Or with
it's with the visualization routine.
Something happened after Toby was playing around a few months ago, whereby there's always this crazy line here.
Yeah, but it's clearly in the visualization.
Yeah, because it doesn't spread anywhere else, I don't think.
Well, I think
You guys see that as well? I thought it was just me. I've been hunting for that.
No, yeah. It's not in the code.
I only checked on Bugzilla, but there was a bug about it, so.
Would you rather bug about it? Yeah. Because
I still don't see that.
this line here is offset.
You can't quite see it. I could show you one. It's a ghost zone, I think. The whole thing,
Yeah.
the whole.
It's a
whole
shearing
sheet
ghost
was
zone.
offset.
Yeah.
It's a shearing ghost zone coming in, right?
No, that's exactly what it is. It must be something.
It's the first ghost zone from here.
Yeah.
That has somehow come in here.
And didn't we figure this out in New York? Or did I figure it out and not tell you?
I could have forgotten that honestly.
But what is that?
But yes, I saw it
The
in Craig also. I
article.
didn't write a book and forgot
there
to
too,
go
yeah.
back and sort it.
Yeah, but
I think I did figure out that it's
Okay.
offset by 1, some index somewhere in the.
But there's something wrong with the video file. I think it's outputting somehow one shifted to the right, so it gets a one ghost zone.
What directions is that? This slice?
X and Y.
X and Y, so it's offset in X.
Yes, I would say there's some kind of index problem in X.
And that's a slice of.
It doesn't matter if that's a density slice.
It's a density slice, yeah.
Yeah.
But wait a moment. I mean, the video files they don't write ghost zones.
They shouldn't,
They shouldn't right now.
but it seems that they are, at least after Toby was playing around last
I
time.
mean, how's it possible? I thought, I mean, the size doesn't even fit.
No, it's just offset. Instead of writing from L1 to L2,
Oh,
it writes
okay.
from L1 plus 1 to L2 plus 1. That's my guess.
Crazy.
Yeah.
But it doesn't.
It doesn't?
Because that was my first reaction. I went and looked. They're all L1 to L2.
Then I have no idea what it is. It's definitely not physical. I mean,
But L2, but L1, L2 in IDL is not the same thing as in a Fortran, right?
No, but this is actually the data written to a file.
Yeah, it's not.
The data is the correct size and everything. So it's what the code outputs is that. IDL is plotting it absolutely correctly.
oh yeah, I would guess so. I would just guess
Yeah,
that the
the
code
index is wrong.
is writing from something to something, and this could.
Oh, I know where it is.
Oh, what?
Aha. Right, the only place I have a look.
Should I continue writing this in the Bugzilla?
Yeah.
That was only one
I'll fix it
video.
all through with all of it.
Yeah.
But if I don't, I'll forget about it. So
Have you found it?
yeah.
Then I can put it up on the screen and we can all laugh and point fingers at it.
And what you can put it, you found it all the boat.
I can put it on the screen if you tell me where it is, and we can all laugh and point fingers at it.
And see what CBS annotate.
You want
No,
to pull out the...
No, I'm looking, but I have
Alright.
narrowed it down. It must
Okay.
be.
Anyway.
I've hunted slices and all. I've been all the way through the slice code because we implemented this new slice stuff. It's not there.
Good, so you...
I will just
you're doing
continue.
the break. Right?
I'll just continue. There's only 2 slides left or something. Timings, of course, is interesting. So this is a 64 cube self-gravity problem and a 128 cube self-gravity problem. This is exactly the 1 over number of processes, I would guess. So not the number of processes. And right. So this is 4 processes. This is 8. This is 16. This is 32. And let me just think what I'm actually plotting here. Okay, this one here with the star is with self-gravity and with the plus is without self-gravity. So first of all you can see that the for 64 cubed I just take here for 4 processes you have some kind of time per time step per mesh point, and then this straight line just shows what the perfect scaling would be, right? That
So
would
there's
be
an offset somehow, is that?
that means that it's slower. It does become, yeah, that's a good question.
Oh, right.
It does become, yeah. It seems to scale alright, but it seems that there's some kind of offset setting in it. That's actually a very good question.
Actually, maybe also you want to plot this double logarithmically, no?
A double dot.
Yeah.
Is that what you're doing wrong? Maybe that is.
What's that?
Normally I plot these things in the double log plot.
Yeah, log for example.
Oh, it's supposed to be log log. Yeah, okay.
Is it log log?
No.
It's usually log, but that's
But log log would show you a straight line.
yeah. You want to see how close to a power law it is.
Yes, of course, yeah. It should be log log, but it's not. Let me just redo this first briefly. It will make more sense actually, because I have the data here somewhere. Did you find the bug term?
No, I've just realised that where I thought would be actually physically can't be. Because my thought was, of course, the read video files have been frozen, but if it was a read video files problem, you'd see it at every processor boundary as well.
Yeah, and also it's in the the expander.
So read video files doesn't touch it.
So you want
Well, we could still be able to read video files, but presumably it would be a little surprising. I mean, someone could have screwed up an index in X and read video files just as well as they could anywhere else. I mean, that does actually create the file, so it's possible, but it's it would be strange.
Oh, okay. But it should also be a straight line in linear, right?
Yeah.
Okay, that's what it means. But okay, I can do it log log also. Let's just check it out.
You'll complain if you've got X range north.
Oh yeah, you're absolutely right.
Preemptive debugging there.
Oh, I don't like that.
Fun one, yeah.
And why would it say so? Okay. So what are we learning
Now.
about this? That it does seem to be. Oh, okay. Now we can actually see that
The two compare, and the two both give the same.
Yeah, but it's a different. It is a straight line.
But
Right?
first of all, why do you see number line up going up? Oh, it's 1 over the number, yes.
Yeah, and here we see it is a straight line, so it's just a shallower power law. So it just means a bad scaling, right?
Right.
Okay. So I think A log log is probably.
Okay.
And why to plot it 1 over number instead of number itself?
Well, time
Because
you always plot speed up, right?
Yeah, but now you can actually do it. Now it doesn't matter because
Now it doesn't matter anymore. That's
maybe
true.
you want to do it first?
You're right.
It's more familiar than it was.
Yeah, like this. Right?
Yes.
Oh, it's one of the CPUs. I didn't read the bottom.
That's the only way to make the line
Make it
in
linear.
linear.
Yeah, okay.
Plot, right?
No.
And then we probably all don't need so much here.
Per stack per step per point, right?
Time per mesh point. Okay, let's try one more.
US per PP per point.
Oh, I did like that.
Can you do a line thickness of 4?
Sure, this is the only way to make it linear. I mean, you could plot a number, but in a logarithmic way, right? So then you would appear linear.
If that's also what I'm doing, right? Or what's happening now?
Yeah. says now it has 82 infections. Okay, but then when I actually do the scan, it says 0 infections.
Aha. So you need a magic bullet.
What?
You need a magic bullet from you. A magic bullet is a virus scanner on a known clean disk. You actually boot the disk. And so sometimes most viruses, the first thing they do is they go and disable your virus scanner or cripple it.
Uh-huh.
So the virus scanner can't find it. So the only way to scan a computer where that's happened is you actually have to you can actually get magic bullet CDs. So you can make some virus scanners like Norton, when you install it, you can find it and install it. But you must do it before you've ever been infected with a virus, of course. And then you keep the CD. Because as soon as the computer boots up, it loads the virus. And if the computer loads the virus can disable the virus scanner. That's the kind of thing that happens, right?
And the FCQ wouldn't notice it, you mean?
Well, exactly. If the virus that FCQ hasn't updated for yet, one of the things the virus could do is, so for example, it's quite common that FCQ, it's quite common that the virus will disable the updates of the virus scanner. It makes it look like it's doing the updates,
but I mean, then if that's the case, then FCQ is rather stupid, of course.
Well, no, all virus scanners are.
I mean, but you say that it hasn't been protected for this particular.
Yes. So it's like when you get your measles infection. If you get measles before you've had the vaccination, then you're going to get measles. Now, if one of the symptoms of measles is that the vaccine doesn't work anymore, well,
And that's what it is.
Yeah, there could be. That's common, right? Although I don't see this very often. I'm amazed how few viruses are, as Toby was saying, they don't seem very destructive anymore. There's lots of viruses that just seem to suck information off you.
Maybe you should have a look at this then.
Oh no, don't say that.
No?
The same thing happened to Angela's computer and I lost 2 days fixing it.
Okay.
So I tried to persuade her that she should run Knoppix.
How come you say you call it actually Knoppix and not Knoppix?
I don't know, because I've heard guys who... You call it Knoppix? I used to call it Knoppix.
No, I mean the guy's a German man.
So the guy's German, exactly, so it must be Knoppix, right?
Yeah. But I mean, I heard for example people talk about people like Gothi instead of Goethe.
Yeah.
American translation.
Yeah, you use pronunciation. So if you know, you don't, do you? I'm just trying to think of another example.
The same as with Ramskada, of course.
Yeah. Yeah.
Just a second, I'll be there.
Oh, do you do the line thickness?
Yeah, I try with the line thickness also.
Good.
Yeah, it looks like the whole problem is that the whole universe is offset by one mesh point. So I think if you just pick your laptop up and move it along one mesh point, it'll work. I can't find it. It's crazy, right? And I'm wondering if it's something I've changed, but of course I've only done it for one thing. You know, my slice is
I mean,
changing.
you could check out a thing where you know it was working.
Yeah, that's what I was going to do.
And how come none of the so the calculation is not affected by this? Yes.
Oh, I think not. Then I think the auditors would have found out.
Alternate slices.
Yeah.
But they're very rarely edited, so the slices code, or it will be very rarely edited once it's abstract and you don't actually edit the slices code, you just implement the slice.
But also we don't have all the tests on any of the IDEA routines, of course. That's probably okay.
Okay, let me just...
Minor. Okay, that looks good.
Yeah, right? And then I can do... Let me just rename this one.
Okay. Actually, the other one was even super linear.
Yeah, let's just check this one.
Was it a line one?
You don't use PSE, PSI then? PSI, PSE.
No, I never got used to it, but I know I should. This is just too much work
Yeah.
and copy pasting stuff. Oh wow, I love this one. Ah.
What's the advantage of using /xdoc instead of /_oo instead?
That you've already got a plot command.
What is underscore O?
Oh yeah, it's just a synonym for /xl.
Oh, plot O. Oh yeah.
And of course /xl/yl is sufficient as well. I can never decide if that's a feature or a bug of IDL.
Well,
What?
So the minimal variable name, you only have to put the minimum amount,
it's not a bug.
but it's unique.
It's really annoying, right? Because sometimes it will tell you that there's an ambiguous keyword.
Yeah, but then you know, and you've done it too much.
Yeah, but you cannot have the keywords x, xx, and xxx, right?
Yes.
Because then say x equals 4, it says this is an ambiguous keyword.
Yeah,
That's the difficulty with it.
That's what I hate.
You can't choose any variable name.
Yeah. I think it's awful.
No, there are cases where you really do want to have
Oh wow, look at this.
something and something underscore the birth. What? Like variable and variable underscore parameter as two variable names. You know what I mean? So you've got like, you might want to have x be an array of x, but you want x underscore 1 to be 1 upon x. You can't have that.
that's a keyword.
There's keyword arguments, yeah.
Right.
I've found several cases where I want to do it and I can't.
Yeah, the X is ambiguous now. Somebody just thinks that. Touch talk.tech.
Yeah. I use this.
What was that?
I use LaTeX to make a PDF file, so that there's.
Oh, and it wouldn't compile if you just change. I mean.
Exactly. It doesn't depend on the figures. So
Figures,
the
yes.
pack is basically called PDF screen. I don't know if any of you know it. It's pretty old,
Yeah.
but very basic
yeah.
and kind of nice.
Is Wolfgang still using that? Probably so, right?
No, I think he's
PDF
using,
screen.
was that, did you recognise the presentation of thing Wolfgang gave? That's not Vue, is it?
That was just HTML, right?
Yeah, that's right.
Didn't look like it to me.
Oh,
What?
I thought you'd done latex to HTML on it though.
I think it was just an HTML talk. That was my impression.
Yeah, but you don't write the talk in HTML, right?
Why not? It's excellent for it, right? I mean, you can do bullets and you can have figures and you can. It's easy and I mean, why not HTML?
The syntax is just like. Every time you want to do something, you've got to do wrappers around it.
It's actually worse than doing Microsoft.
By the way, the Pencil Code website is all wrong.
Oh, wrong?
Is it? Yeah. It's like it's got open a paragraph, but the paragraph never gets closed.
Yeah, I see. So do you have the software to fix all these bugs?
Yeah,
There's
you've got
there's
VI.
Huh?
VI is the software to fix all that.
But there's something better actually. You can actually run it.
You can run a scanner to scan proof the thing exists, but then you've got to use VI to fix it.
Yes.
Because the whole point is it doesn't know where to put it.
It's actually amazing how all these browsers, they don't care really, right? Very forgiving.
They just guess, yeah.
So there's no way of actually figuring it out.
Well, you use the HTML validator, right?
Hey.
You know this,
Maybe
right?
no, maybe that's the one I forgot about. I knew about this perhaps, I think.
So www.w3c.org.
Okay. I'm back.
Alright then.
So these are the timing. As you see, it's a 64 cube. So this is without zero gravity. This is with zero gravity, and this is the perfect scaling. So you see that it is a shadow of power law.
Yeah.
And that must because of the communication involved with the.
Okay. It's not so bad, right?
Okay, it's the same resolution, so it must be the communication. If that's the only, no, it's not bad.
I mean the slope, especially in the 128 cube thing.
Yeah, it's just perfect, right? I mean,
Yeah.
What's the line you plotted there? One.
this one.
Is that
That's a perfect scaling from the first from the
from the
lowest.
first point, right?
Yeah.
Perfect scaling from where?
From the first point. So
Well, what happened with the 100 ones?
This one?
Is that a bigger problem?
Yeah, the last.
It's not linear, right?
This was a 128 cube.
You don't see the lower dot because you cut off the Y range.
Oh, this one.
Yes.
It's just down here somewhere.
Right.
Right.
Yes.
But isn't the last point there kicked upwards somewhat?
Yes, it is.
This one?
Yeah.
But it should, right?
I mean, yes.
It should at one point because there's too much communication.
Yes, I mean
the FTP solver is drowning in
Right. Yeah.
communication.
So
It
wasn't that. So
it's just this effect here. You just see coming here probably.
yeah. Somehow, really, with these tests, not only have you got to do, you've got to put that picture alongside one where the problem size per processor is constant, right?
Oh yeah, yeah. But
And I mean, a cheaper way of getting around this is to take always the minimum for a different number of processors, or plot them all on one graph, and you see which one is the fastest. And of course, larger meshes will be faster eventually.
yeah.
And what the topology of the processor? How much processor you put in X direction, in Y, and Z?
I didn't consider that at all. So my normal experience is that it doesn't matter. At least for the computers I run on, which is not the horseshoe anymore so much.
Yeah, in the manual it says that there is a huge difference, right? If you put some number in Y and another number in Z, that says that there is a difference of like 17. Yeah, like.
Which there is. It also explains when and why that happens.
Yeah, that's problem.
Yeah, but I remember someone telling me that it was.
Well, it depends what cluster you're running on. If you're running on a MirrorNet cluster, which is a perfectly connected network, it
It's
doesn't
something what?
Something not to be trusted completely because it
Yeah, but
doesn't matter much.
But it does depend on the layout, right? Of the computer. Of the layout of the computer.
One should test it for. Ideally, one would get access to a supercomputer and
how
then test it.
how the layout of the processors are.
I mean,
right? I mean,
because it shouldn't be for always. Maybe it's 8 or.
you have your
The delay, right?
you have your you have CPU, you have processors, right? I mean Linux boxes. Each Linux box they are just like these. They have the floppy disk drives, they're completely standard things, all in their usual casings. And they're connected with switches like these.
Well, they are horseshoes. Usually they're rack-mounted things.
And you have fast Ethernet. Fast Ethernet is supposed to be fast, but it means actually 100 megabits per second.
Yeah.
So that's of course nothing by comparison with these more expensive machines. Okay, so you are limited by communication eventually, and then it depends.
Latency between any two nodes is not necessarily the same, depending on the structure and topology of the network.
No, it has to do with bandwidth really.
Yeah. But how do you guys measure the timing things that you say that are on the menu? You know, like
Which
that
guys?
you can have a factor 17.
So you run it different ways.
Change. Yeah, but
You run it
how many problems have you tested? Was it one single problem which you guys did it, or?
I mean, it could actually have been.
No,
I did
it several times.
You also did this?
Also,
Okay.
It's just a matter
On a different
of
computer
that
then, yeah?
specific
I did it on Horseshoe and on, we
Right.
did it on, I know that on Copson,
Okay.
which is mirror-netted,
So
the effect was almost null.
Yeah, but that's because you have a completely different network, of course.
Exactly, but it's a pseudo perfectly connected network.
So it's not problem dependent.
It's not
No,
necessarily
the
problem
the
dependent.
communication
It could
should be
be
the
different.
same, right? No
It
matter
could
what
be problem dependent, but I think
you're solving.
So then, whenever one solves something, one different supercomputer, we should test it there.
Yes.
Right.
Correct.
Okay.
Ideally.
You did.
No, I never tried. Yeah, I did at one point, yes.
I mean, often you don't even
I don't
test
often do
it.
it.
Think, when this problem appeared, which was 2001, 2002, it was quite early on it appeared. And there was one point where we considered, well, I considered, and some people were with me, we were going to write a script so that rather than just randomly use, at the minute the tensor code just takes whatever processors it's given. The first one becomes the first processor, and then it marks them across the box.
Right.
But what we're going to do is run a very quick latency test and test the inter-processor communication speeds. We'll do at the beginning of the run, do a quick sample, and then say, right, it would be best if we laid the processors out 1, 3, 4, 7, 8, 2, and that will give you the optimal communication. But then it seems, as computers have progressed, less and less this seems to be an issue.
Anyway, so one thing you see from the timing is that the difference between no gravity and no self-gravity and self-gravity is actually larger with a higher resolution. So it doesn't, in a way, with higher resolution, self-gravity starts to become more and more expensive. But that's also what we expect, because it doesn't scale with n as the entire code should, but it scales with n log 2n. So there's a small difference there.
So what is the factor?
Yeah, that's a good question. It seems to be. Let's just look at the numbers, maybe.
Now you can just measure the vertical shift.
But I have all the numbers here, right? So I think that might be easier. Okay, so this is kind of self-explanatory, right?
So it's less than a factor of 3.
So here's a factor 2 difference between 64 and 64 no graph.
Yes.
And here suddenly the factor's more like 3 when you go to 128 cube. Which is, I'm actually a little bit worried about that. Because log 2 of 64 should only be 8, and log 2 of 128 should be 9. It should only be a matter of like 10%, right?
Yeah,
So I'm not.
reason then.
I think I would have to redo these again to be really certain
Yeah.
that this is correct. But anyway, it seems to that the self-gravity takes on the order of the rest of the code. So
So the mean factor is 3 between no gravity and gravity.
Yeah, it is at least for 128 cube, but if you go to 64 cube, it's more like 2.
And there's no MHD here, right?
There is probably no MSD here. You're right. So it means there are not so many bad cross terms and so on. This is a pure hydro self-gravity problem. So, and at least it shows that you can do self-gravity, and okay, your code becomes two times slower or something. We can all live with that, right? So.
Okay, now let's hear about the main tricks.
Yeah, okay, I just want to tell a little bit about particles. So the main science goal of this, it's been a program goal and a science goal, and the main science goal has been from the beginning to put self-gravity on the dust particles in the shearing box. Because when you have dust particles in the shearing box moving in magnetomotive turbulence, they are really concentrated a lot in the turbulent flow, and we wanted to see if these concentrations could become gravitationally unstable. We're talking about meter-sized dust thingy moving in turbulence. And I'm not going to talk too much about what we have to do with the particles. I can say the Fessenden code is now officially a particle mesh code. If you go to Hockney and Eastwood, famous book, that's we can now officially call ourselves a particle mesh code also. After what Jeff and I have implemented for letting the particles feel their own self-gravity. So
Pick or not? You call it pick then or not?
yeah, sometimes you do, but yeah, you always call that pick.
You know
particle
Jack,
itself?
what's the acronym PIC? You know when that exactly applies to code?
Particle in cell,
Yeah.
cloud in cell. I have no idea. We went through this.
Yeah.
It seems to me that from what we've figured, PIC is something that plasma physicists like
Yeah.
counting.
Yeah.
And whether or not it has a precise definition or if it's just cultural and it means cloud in cell.
Let's say it's the same. And PIC is a particle mesh code, right? Particle in cell.
I mean, it's certainly the same in terms of, generalities. It's a particle mesh code.
So the main part of particle mesh code is the assignment and the interpolation step. So the idea is you have a lot of particles, you want to calculate some force on them. So first you assign them to somehow to the grid. So you can either say that a particle just is at the nearest grid point, the so-called NGP method, or you could say that you could go to one higher order with the cloud and cell method, where if a particle is halfway between two grid points, it will be half in each of them. Or you can go to an even higher order with a triangular shaped cloud, where each particle is like a triangle. So it peaks its density where it is, and then the density falls with the diameter of
It's true. It's a triangle in its in amplitude.
Yeah.
Not space.
It's cone.
Yes,
It's
so
a pyramid.
That's a hypercone.
That's right.
It's a pyramid in 3D, I think.
Well, it's a
Hypercone.
It always points in plus one direction.
That's a hypercone.
Right.
Okay, cool.
Right.
Yeah,
Well,
it's a
it
hypercone.
would be a cone in a 2D one. It would be a cone, right? So
Yeah.
it must become the hypercone in 3D or something like that.
So the idea is to solve the Poisson equation on the mesh. So first you take all the particles and you assign them to the mesh with one of those. All these three methods are implemented now. And then once you have the particle density defined on the mesh, then you just solve the Poisson equation as always. Then you get the potential defined on the mesh point. And then you want to go back and say which force do the particles feel. And then you can actually again use these three because you will realize that this one is actually a second order spline interpolation, this is a linear interpolation, and this is just again nearest grid point. So you can kind of use this for the interpolation also. And one thing that's important is, at least according to Hockley, that you have to use the same scheme when assigning as you do for interpolation. This way you are completely sure that there's mass conservation and there's no self-acceleration. So if you were to use, for example, the TSC for assignment, and then I think I can do that. But if you were to use like the nearest grid point for assignment and then interpolate it back to the triangular shaped cloud, you can actually show that the particles would then feel their own self-gravity and would start probably moving to the center of a grid point or something. So it's very important to use the same order of assignment as you use for interpolation. I don't want to talk any more about that, I think. I just want to show we actually have a test problem also for dust particles, and that's just the pressureless Jeans problem. So the dust particles don't feel a pressure, but they feel a drag force from the gas. And so again, we are bounded position and drag force, and this is the dust velocity feels its own self-gravity plus a drag force, which is so just assume that the gas has velocity 0. So whenever the dust has a velocity relative to the gas, it's kind of break down all the time. And there's actually this funny dispersion relation coming out of it. If you solve this one for omega, you can see that dust grains are always unstable. The dust fluid, the dust component is always unstable. Only that if the friction force is very if friction time is very low, the growth rate can be incredibly low. That means that they might feel attracted to each other, all the dust grains, but they can't move because the gas is stopping them all the time, right?
That's like the Jeans criterion is sound speed equal to 0, right?
And a drag force. So you have sound speed equal to 0, and you have a drag force, which is effectively a velocity limiter. It means that there's a terminal velocity. You cannot move as fast as you want to.
Somehow naively one would have thought that maybe the particle dispersion could act as a temperature.
It can. Probably, but that's not in the. I mean here in fact these equations. That's why I always write W here is actually the particle as a fluid. So when you solve with particle with actual particles, with particle behavior, where in a single grid point they can have all kinds of velocity, then there will be a pressure from the particles which can destabilize them.
Okay.
And I just want to mention that there's a test problem here, and we also get exact correspondence with the linear values. And this is what does treat as particle with the triangular shaped cloud, which is a second order interpolation assignment methods. Okay, science. This is the last slide. I just want to show self-gravitating dust particles in MRI turbulence. I will show a movie. This is the of color density of dust, and this is the x direction, this is the y direction. So it has been averaged over the z direction with the. No, it's been averaged. It has been averaged. Yeah. Okay. So it's not color density, I'm sure, but it doesn't matter since it's a contour density.
Yes.
But it is actually the average, but we can.
All of these are both time constant.
Yes. That is absolutely true.
But I'm actually using these 2D averages that I implement in the code, which I found very nice. And I also did a reader for them, PC read ZAVA, which is more like a movie player actually. That's mostly what I need it for when I have 2D averages. Okay, so let me just show the movie. Okay, so from the beginning you see nothing.
Could you minimise the talk or something so the background's not white?
Yes, I can just.
So it makes it really hard to see somehow.
Yeah.
We can better do it, but
Maybe not.
So actually, this is the time, an orbit is 2 pi. So at the time of 10 pi, we turn on the self-gravity on the particles because when the turbulence is setting in, all kinds of funny things are happening. We don't want the particles to be gravitationally bound all already there. We only want to have it once you have a self-sustained dynamo-driven dynamos, well, not dynamo-driven, but dynamo and MRI situation. Right? This happens for around 10 orbits. And I hope you can see this. Just wait. Oh yeah. So now you see that. Oh, that's the whole. Okay. So this is the dust density, and at one point you see 2 gravitationally bound structures. That. Okay. Let's play that again. I will just.
Possible to slow down the frame rate on this?
I think I'll just stop it somewhere. You see the thing there? Okay. So this is the typical thing you get without self-gravity, that all the dust grains align in these big sheets. And these big sheets more or less correspond to places where the gas density is a little bit higher than average, only a few percent higher than average. Because in these regions, the gas is in some kind of equilibrium where the pressure gradient, whenever the gas density is a little bit higher than the average, it gets into some kind of equilibrium where pressure gradient and Coulomb forces are in balance. But the dust grains don't feel the pressure gradient, so they have to pile up in there. And this is what we typically normally see. But because of the self-gravity, you will see now that this sheet starts to collapse into 2 distinct clumps that at one point meet each other and collide and become one clump. So you see one clump forming here, and there's another one forming, and here they collide, and they stay together.
what is the mass of these clumps?
That's a good question. So this is about 1 scale height cube. I think it's around, if you take all the solids in there and put into one clump, it's like a 1,000-kilometer body or something.
1,000-kilometer body?
Yeah, like a protoplanet or something like that. Sometimes
like
the
an
typical.
asteroid?
Hmm?
Like an asteroid?
More like a protoplanet. I mean, the biggest asteroids are 1,000 kilometers, but normal asteroids I would say 100 or 10. Right? So it's more like a protoplanet. I don't know how massive do you have to be to make a
Giant planet?
to make a gap. Then you have to be very very massive, right?
It actually
Well, it depends on the gas.
viscosity too.
Yeah. I think we are in the range here of I don't think this guy could make a gap in a disc or.
No, I don't think that
Not
would
that
even,
one, yeah.
I don't think that would even significantly type 1 migrate either.
No.
But we'd have to check. Well, in the paper we should check this.
But then, do you also allow those things to accrete gas?
Nope.
No.
Not yet.
How complicated would it be to make those
Extremely.
separate gas?
Yes, an extremely good question. I've never thought about it.
I think it would be kind of impossible.
Why?
Because they're particles.
So?
It's smaller than, I mean,
You can
much.
keep gravitational.
Oh, you mean turn them into like sync particles?
Yeah.
Kind of
Yeah,
suck gas out of the
yeah.
flow. Oh.
That's what I mean.
That
But
would
they need to grow in their
We
mass.
could definitely do
Yeah,
that.
of course.
That would definitely be possible.
I mean,
No.
the moment the masses of the particles are individual, right? Or what?
Yeah, we could.
Are they?
Mass
It's
of
all the same
particles.
particles.
Yeah.
All the same mass.
All the same mass.
So that's another thing.
You are dealing with meter-sized particles, right?
Yeah.
That's the other thing. They're not actually turning into one particle. There's just 10,000
Yeah, it's a
particles.
bound thing, right?
Yeah. Yeah, it's just like.
You have to.
Oh, you don't actually replace it with one massive
That's
particle?
what I'm saying. You don't do that. It's just
No.
they're sitting there bound at the moment.
I think
You could do that.
that's kind of
That's
the next
right?
step
And then you
of
really
technology.
improve
Right?
your
Yeah.
speed somewhat, right?
Yes, exactly, because
Dramatically.
you cannot get them apart anymore, no matter
Yeah,
what you do.
this is the standard, SPH star formation game.
Yeah, sure.
You
Yeah.
replace it with a sync particle, and then it starts accreting gas.
Yeah.
Understand. How many particles are you using there
2 million.
for that? 2 million particles.
Yeah.
So then, what's the difference from solving the Poisson equation to assigning a gravitational pull to
show every single particle that you have there.
Oh, you mean like an n-body?
Yeah.
That is scales like n squared. That's the difference. You have to do n squared calculation. If you do the direct summation over all particles, you have for each particle you have to sum over the position of n other.
Yeah.
That becomes n squared, and that scale is awful. I mean, that's something you can do with 1,000, 10,000 particles.
It's actually worse than n squared, isn't it?
Yeah, it's overhead.
It's worse than n
Yeah,
squared?
the overhead of actually doing it, it's, I mean, aside from the silly issues like cache efficiency and things, it's just really, really slow.
I mean, unless you have a room full of great, there's no way to do it.
But even then,
Even then you're
1
not
million
correct.
particles n squared, I don't think anyone has done that. Or
Oh, sure.
Oh yeah, there's lots of code that have done it, but
oh, okay.
you end up, you do it when there's a few very massive bodies. You don't do it like this.
Yeah, and you also don't do it for these kinds of times.
Yeah. Right.
I think.
So this is, I mean, yes, turning things into a Poisson equation is a simplification.
Right.
I think it's a very valid one. It means that it's. I mean, the problem is this guy cannot collapse anymore now because it's just one grid point filled of the particles. It cannot fragment on something on a smaller scale than.
Of course, again, the next step as well is that you introduce these sync particles, they become massive and it becomes a planet, and then you say, okay, I've got 10 planets and 2 million particles. Ah, well, there's a Poisson solver for a potential plus 10 Newtonian potentials.
Yeah.
Yeah, or you know,
there's also sometimes people solve like a particle mesh self-gravity on an adaptive mesh. So that they say whenever a certain grid point has like too many particles, you just cut it in 8 immediately, and then you count it in individual 8 and so on. But then also we couldn't do it with a Poisson with a FFT solver anymore. You would have to go to a multi-grid one or something.
This is also quite complex.
Yes, it is.
The technological challenges involved in mounting all of these things that we just talked about are.
So I think a lot of things can be improved. But
Yes, that's
everything can be improved.
but we seem to have technology state level 1 in place at least, and we hope to do one publication at least before we start improving a lot on the code.
Yeah. Oh, definitely. I think this alone.
Yeah. Right.
We found.
You realize this communicated mesh thing would work trivially. Right? Oh no, you have to explicitly handle particle transitions between meshes.
Explicitly handle particle handoffs, and that would.
But no, but you already do this. You already handle transitions of particles along boundaries.
That's right.
It's trivial. It is literally trivial.
But
It's just another interpolation technique instead of because you have as well as having a rectangular, so as well as the usual rectangular interpolation to do onto the new mesh. You've also got to. No, there's no interpolation to do because their positions are their position. So actually, particles work through the multi-grid even more trivially.
What are we talking about?
Sorry, this parallel.
Yeah,
The nested grid reference.
Oh, okay, the particles will have.
I was just thinking, you're saying that this is actually quite complicated technology, but the hierarchical stuff where you can say this complicated technology and it runs underneath this complicated technology, you get this incredible power, right?
Yeah, I think that would work. But just the more complicated parts about sync particles and replacing them with Newtonian potentials. Sync particles themselves are quite complicated beasts because they not only have to have free mass, they also have to have angular momentum. And keeping track of all these things means you have to have a particle has to have a much larger data structure than the particles we have right now, which are essentially.
Now aren't you glad I made you implement that nice general thing that could have particles with all kinds of properties?
Oh, yeah.
Do you remember? The original particle were just going to have x, y, z position and maybe their velocity, right? That was it.
I don't remember that.
Yeah.
He's always telling stories about everyone else, right?
That was the original, right?
Science question here.
Yeah.
How do you do that when you have collision of the two gravitationally bound things? Because they can also break, right? When they collide. So they need to depend on the energy.
But it's not a solid body. It's not surface forces holding it together. It's only gravity. So it's like a star cluster or something of things moving in and around and between each other. So it's true you can break things, right? I mean in reality, once you get a pretty high density of meters, I think they also collide a lot. But it's actually beneficial because that will cool down. So if you have inelastic collisions, then you can whenever. So as Axel was saying, any root mean square velocity in the dust particles will be stabilizing against self-gravity collapse. But if they start colliding and dissipating energy in the collision, that would really mean that you can cool down.
Yeah, well, what I'm asking here is that once you have a gravitationally bound bunch of particles, do you allow single particles to leave it?
What do you mean allow? I mean, yes, if it's possible, right?
Yeah.
But
Can they leave?
Of course they can, because you have a turbulent background field and some turbulent flow will come around and just sweep off.
You get really powerful shear flows. You know, it's only marginally bound, it'll go.
And you have
shear flow a little closer than it would without self-gravity, but the shear can still win.
Yeah.
It's just in this case that self-gravity wins.
Right.
Yeah.
I mean that depends probably on the minimum radius that they minimum separation they can have.
Between
For
particles.
the smoothing length. You have smoothing lengths, right? That limits the proximity of the two neighboring particles.
What?
You have a smoothing length in the potential.
The smoothing length is the grid scale.
It's a grid scale, yes. Right.
Yes, that's
yes.
true.
And so if the shear then was to overcome the forces over the length of the grid, then they could maybe.
That happens. We have seen clumps that are transition features. So they live for a while. They dance around each other for a while, and suddenly they get too large with radius then, and they are being sheared out again.
Good.
I mean, this can definitely happen. So one issue is actually that the assignment interpolation scheme has a tendency to underestimate the potential at the small scales. So I think, for example, when it comes to resolution, actually going to a higher resolution would probably mean that at these kind of scales you would feel a higher self-gravity because there's of course there's a discretization error also there.
Yes.
And it's not even sixth order, it's more like second order.
Yes.
So it's a lot of errors there. So I think it's likely that we're underestimating self-gravity at the small scales actually.
And then the time scale is strongly changed by the MRI, or time scale to get I don't know a certain level of density of total particle density.
It wouldn't happen without MRI.
Yeah.
If there was no MRI and you just put in these dust particles in the shearing flow, they'd just be shearing. You need the MRI to do something turbulent that would just transiently concentrate dust grains somewhere, and then let self-gravity take over from there.
It can have the change in stability, no?
The gas or the
Yes, for the gas.
no, because the gas is so pressure supported. So we try to run these simulations with self-gravity on the gas also, and it doesn't make any difference. So even though the gas here would feel attracted to this clump, the gas is so pressure supported that it doesn't really. I mean, it just means that the gas pressure in there increased by 0.01% or something, and then already there it would be strong enough to keep the rest of the gas from coming in. Right?
Okay.
So it's really important that the dust doesn't feel a pressure. Doesn't feel so the dust grains don't mind being close to each other. And
but in a global disk, that thing can change, right? You can have density clumps there in a global disk, so then you can reach gene masses in some parts. Yes, that's how Bose makes giant planets, right?
If you have an extremely unrealistic cooling, then you can do that.
But then
I've got all this now.
Make up crap.
Yeah.
But he's not running MRI, is he?
No, it's a marginally he starts with a marginally unstable gravitationally unstable disk, and then he gets it evolved. Yeah. But the issue with the gas is not only that it has trouble colliding, collapsing even when it is gravitationally unstable, and it does collapse. It heats up so much in these clumps that it's really difficult to do anything unless you can cool them like very efficiently, which I think the pendulum is swinging in the direction right now where people say that it actually come.
You can cool using radiation, yeah? And then you can have radiation now.
No, but
Yeah, we talked about doing exactly that.
You can cool
gas
with
simulation. Not globally, it's locally.
Yeah, because I read also that metallicity is very important for the cooling, and then
of course, yes.
No, actually people find that metallicity is not important. Okay.
Yes, of course, because
But you can make your lines optically thick, and then it doesn't matter anymore. You can have your optically thin metal lines whereby you can cool, but I think most of the metal lines would be optically thick in a probe plant like this. That means that metallicity should have very little effect. That's what I hear at least. I mean, metallicity is really important because there's an observational trend that with the higher metallicity you find more and more plants.
Opacity, so
that's the
it
point.
would be an important thing.
But not if you become optically thick. If your metal lines become optically thick.
No,
I don't understand what
But maybe, I mean, it depends on the color, right? I mean, on the wavelength band. If you're talking about a wavelength band that's optically thin, then metals can be very
Most
hard
of
again.
the cooling will be due to CO lines, right? So then,
Yeah.
yeah. So
No, I think
what
also.
happened?
yes, from my naive point of view, I think when you have some metallic stuff in the gas, they can how do you say it?
They can cool more.
Yes, they can cool more.
Yeah.
Because they have a lot of lines, right? They
Yeah.
have a lot of line transition.
Yeah.
But once you have enough metals, once you have enough gas, these lines are no longer optically thin. That means that some kind of photon coming from some kind of metal transition, it will not just pass unhindered to infinity. It will move for 10 kilometers, and then it will be absorbed by another atom. So I mean.
They're very dense and very cold in the midpoint.
Yeah.
Right? That's the issue. So it's different than metals in like a stellar atmosphere.
Yeah.
Completely different region.
I think very
And that
quickly
changes.
your metals will become optically thick, and then it doesn't
Yeah.
really help you so much anymore. It's kind of.
I mean,
There's some kind of balance between the two effects. Some people try to do that,
No.
to simulate at the same time the yeast, the particles, radiation.
Yes.
no, yes.
Yes.
Okay. Cool.
Kai
Yeah, Kai.
Kai and Dawson.
How do you write that?
CAI.
Yeah.
So should we
Yeah.
thank Anders first of all for his very inspiring and interesting presentation?